Okay, so moving on. Previously, we have discussed the terms used in problem solving in reactive systems. Now we're going to deal with material balance. So unlike in reactive systems in Chikal 1, an overall material balance based around moles is not applicable. Diba? Before, for example, this is a distillation column. There's moles entering here, and then there's moles exiting. Let's say 100 moles here. And then this is 75 moles. We can say previously that we can do an overall mole balance. It's just simply N1 is equals to N2 plus N3. But in reactive systems, we cannot do this. Because for example, the acrylonitrile example, I have 100 moles here of C3H6 for example, and then leaving there will just be 70. So where did the 30 go? Diba? So it doesn't make sense. So we can't do overall mole balance in reactive systems. Although you could still do material balance based around mass, because mass is always conserved. So one of the techniques used in material balance with in reactive systems is the molecular balance. So shown is the general balance equation: in minus out plus G minus consumption equals accumulation. So for steady state operations, the accumulation term is 0. Therefore, it simplifies to in minus out plus Gen minus consumption. And then we can still further simplify them based on the circumstances. For example, if the substance is not entering the reactor or the system, in is 0. If the substance did not go out, out equals 0. If a substance is a reactant in any chemical equation, consumption is not 0. For example, simple example, let's say H2 and O2 producing H2O. Since H2 and O2 are reactants, kapag gagawa tayo ng molecular balance, meron silang consumption term. Okay? Next, if a substance is a product in any chemical equation, generation is not 0. For example, here, H2O. Si H2O ay product ni H2 and O2. So this has generation term. So generally speaking, kapag nasa reactant side, there is consumption. Kapag nasa product, there is a generation term. Medyo tricky na siya kapag multiple reactions, because there will be simultaneous of consumption and generation term. Ma-encounter naman natin sila mamaya. So let's go directly with example 1. Ammonia is burned from nitric acid. Ammonia is burned to form nitric acid in the following reaction. So ayan yung hinihingi. Let's go with the calculations. Letter A is very simple. We don't need to do any calculations here. It just wants the ratio of kilomole O2 reacted to kilomole of NO formed, which can be obtained from the chemical equation. So there's 5 kilomoles of O2 needed to form 4 kilomoles NO. That's 5 over 4. Easy. Next. What oxygen feed rate would correspond to 40% excess O2 if 100 kilomole of ammonia is fed? So let's remember, percent excess is fed minus TO over TO times 100%. Percent excess given, this one. The theoretical can be obtained from NH3. Okay, so it said 100 kilomoles of ammonia was fed, so 100 kilomoles of ammonia. And then, based from the chemical equation, 4 kilomole of ammonia is needed with 5 kilomoles of O2. So that should give me 125 kilomoles O2. Theoretical. And then we plug it back here. So 40%. Oh, just 40 should be enough. 40 equals fed minus 125 over fed. 1 over 125 times 100. So fed is 175 kilomoles. Okay, next. If 50 kilograms of ammonia and 100 kilograms of oxygen are fed to a batch reactor, determine the mass of NO produced if conversion of the limiting reactant is 45%. So first, let's determine what's the limiting reactant. It's only between ammonia and oxygen. So 50 kilograms of ammonia, 100 kilograms of O2. And then the single pass conversion is 45%. Of course, the product here is NH3, O2, NO, NH2O. But ito lang ang interest natin. So let's see. Let's start with the ammonia. That's 17 kilograms to form 1 mole. And then, using the equation, chemical equation, 4 kilomoles of NH3 yields 4 kilomoles NO. That's 2.94 moles. Next, how about the 100 kilograms? 100 kilogram O2. That's 32 kilograms to form 1 kilomole. And then, based on the equation, 5 kilomoles of O2 is needed to form 4 kilomoles NO. So this is 2.5 moles NO. So that means O2 is the limiting reactant. So in order to form the mass of NO produced, let's continue from here. I can just multiply this by 0.45. So this is multiplication naman. And then let's convert kilomoles into kilograms. So that's 14 plus 16 is 30 kilograms. This is on the top. 30 kilograms NO. 1 kilomole NO. So that will give me 33.75 kilograms NO. This is also the same. Well, if I rewrite it, it will be just like this. I mean, that's not 2.5. That should be 0.45. There, and then just retain the units. It will be the same there. Okay? Easy peasy. Example 1 is like an example for the terms in the previous video. So let's move on to number 2. Here we have 2 reactions. Ethanol is produced commercially by the hydration of ethylene, but some of the product is converted to diethyl ether in a side reaction. The feed to the reactor contains ethylene, steam, and inert, and then it's also given the effluent gas. So there's the composition in mole percent. What's asked for us is the molar composition of the reactor feed, percentage conversion of ethylene, fractional yield of ethanol, and selectivity of ethanol production relative to ether. So let's draw the diagram first. ang pumapasok is C2H4, steam, and inert. Exiting, C2H4, H2O, inert, ethanol, ether. Okay. Meron na palang nabigay. This is 43.3%, 2.5% ethanol, 0.14% ether, 9.3% inerts, and the balance water, which is 44.76. So these are in moles. Let's set our basis. Basis 100 mole of P. So A, calculate the molar composition of the reactor feed. Let's start with the C2H4. Let's see if we can use the balance. Okay. I'll write here the general mole balance. In minus out plus gen minus consumption is equals to 0. So let's do that. C2H4 did come in as a feed. C2H4 did come out. Is it generated? Well, wala siya sa product side ng either reaction. So that's 0. Is it consumed? Nandito siya sa reactant side in the first equation. So, hindi yan magbabago. So that means in is equals to out plus consumed. So how do we solve this? Well, first, out. We have here the percentage of out, so 100 times 0.433 plus the consumption term. How do we know how much C2H4 was consumed? Well, we have in the production of ethanol, we used C2H4. So that's 1. Additionally, production ng ether needed ethanol. But we know that ethanol needed C2H4. So, kailangan natin yun i-take into account. We need to take that into account. So, the consumption term is based on C2H5OH, yung ethanol, and C2H520, which is the ether. So, here's how we do it. 100 moles. Let's start with the ethanol first. 0.025 mole ethanol. And then 1 mole of ethanol requires 1 mole of ethylene. Okay, it's first part done. Next, 100 mole P, 1 mole P, that's 0.0014 mole ether, and then 1 mole of ether needed 1 mole of ethanol. No, this is supposed to be 2 moles. So that's 2 moles of ethanol. Two moles of ethanol, and then 1 mole of ethanol required 1 mole of ethylene. So I have here the ethanol part, and I have here the ether part. So take into account lahat. So as we solve that, I will get 46.08 moles. Okay? Next. Wait. No. We do the H2O balance first. So in minus out plus gen minus consumed is equals to 0. Water went in as a steam. It went out. Nandito siya. It is generated through the second equation. And it is consumed kasi nasa reactant side siya ni first equation. So, wala tayong ma-cancel out. Let's just solve for the in. So, in is equals to out plus consumed minus generated. So, let's take care of the out first. 100 times 0.4476 plus consume. Again, and in the production ng ethanol, H2O was needed. It's reactant. And in the production of C2H520, the diethyl ether, we needed ethanol. But we know that ethanol required water. So we need to take that into account again. So what I'm going to do here is basically a duplicate of the consumption term we did in the ethylene. So it's just 100 times 0.025 mole ethanol. And then instead of ethylene, it's going to be 1 mole H2O. And then same here, 100 0.0014 2 moles of ethanol is needed to produce 1 mole ether. And then 1 mole C2H5OH required 1 mole of H2O. So this is the consumption term. Next, we have the generation part. So where is it generated? In the second equation here. It's generated alongside with the ethyl ether. Okay, so let's write that. It's minus 100 times 0.0014. And then, well, it's just 1:1. Anyways. So that's the generation part. So let me calculate it first. Plus 100.025 plus 100 0.0014 times 2 minus 100 times 0.0014 47.4. And then the inert is very simple. I'll just do it here. Inert balance. It went in, it went out, it is not generated, and it is not consumed. Therefore, it's just in equals out. So kung ano yung pumasok, yun lang din lumabas. So that's 100 times 0.093, and that's 9.3 moles. So let's complete the table. Okay, let me clear this muna. How did I? Okay, there we go. So C2H4, H2O, inerts. (47.4). Inerts is 9.3. So ang total is 102.78. So the percentages are, this is 44.83, 46.12, and 9.05%. So that's 100. Next, percentage conversion and composition conversion. Well, percent conversion. Well, the percent conversion is just number moles fed minus number of moles remaining over number of moles fed. So it's just going to be 46.08%, 46.08 minus 43.3 over 46.08, which will be around 6%. Fractional yield of ethanol. So fractional yield is number actual moles over moles theoretical. Okay. So since C2H4 is the limiting reactant, let's see, 46.08 moles C2H4, 1 mole. It's just 1:1. By the way, that's the reason why I said C2H4 is the limiting reactant, because in the chemical equation, C2H4 and H2O is 1:1. So basically, they're just going to be decreasing at the same rate. They'll be used up at the same rate. Pero mas kaunti si C2H4 compared to H2O. Therefore, mas maunang maubos si C2H4. Oh, that's it. 46.08 moles ethanol. It's theoretical. Then that means, if I plug it in here, yield is number moles actual, that's 2.5 over 46.08. That's 100%. The yield is 5.43%. Last one, selectivity. Selectivity is just the number of moles wanted over unwanted. Bigay na sa atin what's wanted and unwanted. So, number of moles wanted, that's ethanol, and that's 2.5 over number of moles unwanted, that's ether, that's 0.14. So it's just like that, 2.5 over 0.14, 17.86. That's it. Okay, let's move on to number 3. Given here is the limestone analysis. And by heating the limestone, you recover oxides, together known as lime. So these oxides are CaO and MgO. And that's together known as lime. So there's the required pounds of CaO made from 1 ton of the limestone, pounds of CO2 recovered per 1 ton of limestone, and how many pounds of limestone are needed to make 1 ton of lime. Okay. I'm going to provide na, let's write down muna yung mga reactions involved. Okay, and then we create a block diagram. So this is my reactor. Going in is 92.89% calcium carbonate, 5.41% magnesium carbonate, 1.7% inert. These are in mass percent. Why? Because limestone is solid, and solid, it's convenient for them to be reported in mass percent compared to mole percent. Okay, so these are in mass percent. What's going out? What's going out is calcium oxide, magnesium oxide, and CO2 as gas. Okay, so F gas, and then P basis this time is 1 ton of F. I'm using 1 ton equals 2,000 pounds. Okay, let's answer A. How many pounds of CaO can be made from 1 ton? So let's do the calcium oxide balance. In minus out plus gen minus consumed equals 0. It's not going in, it's going out, it's generated, but it is not consumed. So out is equals to generated. The generation comes from the CaCO3. So that's 2,000 pounds times, we could just diretso na lang natin, 0.9289 pounds CaCO3, and then to convert it to 1 pound mole CaCO3, you need 100 pound mass. Then based sa equation, 1 pound mole of calcium carbonate is equivalent to 1 pound mole of calcium oxide, and then 1 pound mole of calcium oxide is 56 pounds. So this will give me 1,040.37 pounds. That's the answer for A. Let's go to B. How many pounds of carbon dioxide can be recovered per 1 ton of limestone? Let's do CO2 balance. It's not going in, and it is not consumed. So again, it's out plus generated. Now, out equals generated. Now, where will the CO2 be generated from? The CaCO3 and the MgCO3. So we need to take those into account. Okay? So I'm going to start with CaCO3. 2,000 pounds It's basically a carbon copy of the top one, 1 over 100. And then 1 pound mole CaCO3. This time it's 1 pound mole carbon dioxide. And then 1 pound mole CO2. It's 44 pound mass CO2. And then this is for CaCO3. Let's do for MgCO3. 2000 times 0.0541 times, what's the 1:1? 1 pound mole MgCO3, 1 pound mole CO2, and 1 pound mole CO2 gives me 44 pound mass CO2. So after all of that, that will give me 19.86 pounds of CO2. That's it. Okay, let us see how many pounds of limestone are needed to make 1 ton of lime. Okay, so as I pointed out earlier, lime is the combination of calcium oxide and MgO. So it can be done na ito basis is 1 ton, and then just split it between them. So for example, 500 pounds dito, 500 pounds dito, but that would be tricky kasi ikaw pang mag-set nun. So what we can do is we obtain how much lime we get here from this operation, and then we scale it up or down. So ganito strategy. May CaO na ako dito. Let's get the MgO. So that's in minus out plus gen minus consume equals 0. It's not going out. It's not going in. And it is not consumed. So out equals gen. How do we generate MgO from MgCO3? So it's 2000 times 0.0541 pound mass MgCO3 multiplied by, so to get 1 pound mole of magnesium carbonate, we need 84.31 pounds of magnesium carbonate. And then it's just 1:1. 1 pound mole of MgCO3. I just need 1 pound mole of MgO. Yes, so that will give me, I need it in pounds pala. Sorry, so 1 pound mole MgO, 40.3 pound mass. So out is equals to 51.72. So we have the number for CaO earlier, and we have the MgO here. So the total amount of lime recovered is 1040.37 plus 51.72, and that's 1092.09 pound mass of lime. Now we can set it up like this. We know that per 1 ton of limestone, of limestone, I'll produce 1092.09 pounds of lime. I'll replace 1 ton na lang to 2,000 pounds. Now, in order for us to make it 1 ton of lime, we multiply top and bottom by 2,000 because that's 1 ton, as I defined earlier. And then, what we do here is we just do this para maiwan yung 2,000 pounds sa ibaba. So it's 2,000 times 2,000 over 1092.09. So I'd need 3,662.70 pounds, yes, of limestone to get 1 ton of lime. That's it. So you need more than 1 ton of limestone. Okay. Let's go to the next example. This one. So this is from Basic Principles and Calculations in Chemical Engineering by Himmelblau. It's edition. So Semenov describes some of the chemistry of alkyl chlorides, and the 2 reactions of interest are shown below. The species recovered are listed in the table. So what's asked is how much Cl2 and C3H6 were fed, fractional conversion of C3H6 to C3H5Cl, selectivity of C3H5Cl relative to C3H6Cl2, and the yield of the wanted product in grams in terms of grams of C3H5Cl to the grams of C3H6 fed. Okay, so this is a mouthful. Multiple reactions din siya. So let's do the diagram first. So what's entering here is Cl2 and C3H6. Going out is 141 gram mole C3H6, 651 moles of Cl2 pala yung sa taas. This is Cl2. 4.6 moles of C3H5Cl, 24.5 moles of C3H6Cl2, and 4.6 moles HCl. Okay. So basis, of course, given data. So we can start off with the calculations. How much Cl2 and C3H6 were fed? Let's start off with the Cl2. Okay, Cl2 went in, it did go out, but it is not generated, and it is consumed. So the simplified balance is in is equals to out plus consumed. How many went out? 141. plus consumed, it is consumed by this reaction and this reaction. So that's our basis here. I'll use the moles of C3H5Cl. And then 1 mole of that gives me 1 mole Cl2. And then 24.5 moles C3H6Cl2. So it needs also 1 mole of Cl2 for that one. And that will give me how much? 170.1. Okay. Next, C3H6. It's basically the same thing. In is equals to out plus consumed. The same simplification. Nagkaiba lang the values. The values are different. C3H6 that went out is 651. Consumed. So from C3H5Cl, so that's 1:1. And then from second reaction, one is to 1. That should give me 680.1. That's A. Okay. Next, letter B. Fractional conversion of benzene to C3H5Cl. Again, it's fed minus N out over N fed. Okay? Well, lahat given na. Fed is 680.1. Went out is 651 over 680.1. That gives me 680.1 0.043. Okay, letter C. Selectivity of C3H5Cl relative to C3H6Cl2. Again, it's the moles of C3H5Cl divided by moles of C3H6Cl2. So C is 4.6 over 24.5. 0.188. So not really selective. Last one. Yield of C3H5Cl expressed in grams of C3H5Cl to the grams of C3H6 fed to the reactor. Let's just follow that. 4.6 moles C3H5Cl that's 1 mole equivalent to 76.53. Then this thing is divided by, where's C3H6? 680.1. So C3H6 is 36 plus 60, that's 42. So this is equal to 0.0123. Low yield, low selectivity. Not a good process. Pero hindi naman tinatanong is the values. So there you go. Okay. Last one for molecular balance. Okay. So it's the production of chlorobenzene from benzene. So it just describes the process of bubbling the C6H6 in chlorine gas, and then the subsequent reactions. Yeah, the feed to the chlorinator consists of essentially pure benzene in a technical grade of chlorine gas, 98 weight percent Cl2. The balance is gaseous impurities. The liquid output from the reactor contains 65% C6H6, 32% C6H5Cl, blah blah blah. The gaseous output contains only HCl and the impurities that enter the chlorine. Determine the percentage excess of benzene, fractional conversion of benzene, fractional yield of chlorobenzene, and the mass ratio of the gas feed to the liquid feed. Let's do the two input streams. One is pure benzene, which is gaseous. No, actually it's the liquid one. And then this is 98% Cl2. This is the gas stream. This is the benzene stream. So this will be the product stream. And then this is the other product stream. Let's call it P2. So P1 has 65 weight percent C6H6, 32% C6H5Cl, 2.5% C6H4Cl2, 0.5% C6H3Cl3. So the gaseous output P2 in this case contains HCl and the inert. Okay. Let's set our basis. $100 of P1. There's another alternative wherein you convert these into mole percent. So from weight percent, transform them into mole percent. Okay, I'll show you how. So for the transformation, let's assume a basis of 1 gram. Okay, so that means there's 0.656 grams of C6H6, 0.32 grams of C6H5Cl, 0.025 grams of C6H4Cl2, and 0.005 grams C6H3Cl3. You convert these into moles, right? You get the total number of moles, and then to get the mole fraction, you just divide the number of moles over the total number of moles. So for example, C6H6 is 72 plus 6, that's 78. divide by 78. Tama ba? 72 plus 678, yeah. 1 over 78. So I'll get a pretty low number. .00841. C6H5Cl is 72 plus 5 is 77 plus 35 is 112. So that's 0.00286. C6H4Cl2 is 72 plus 4 is 76. 76 plus 70 is 146. Yeah, 146. So that's even lower. And then what do we expect from C6H3Cl3? It's going to be close to 0. So that's 35 times 3, 105 plus 72, 179, 177 plus 3, 180. Yeah, 0.00000278. So to get the mole fraction, the total is, let's see, .013. So this is 64.7% or 0.6470. And then you do that for the rest of this one. Okay? But I'm doing mass basis just for the sake of it. You can do a mole basis if you want. And then you have to convert this into moles as well. Okay. Okay, so we start off with, it's not chlorine, it's supposed to be benzene. Percent excess of benzene. So let's do this benzene balance. In minus out plus gen minus consume is equals to 0. It goes in, it goes out. It's not generated, but it is consumed. So in is equals to out plus consumed. Out. We need this in terms of moles. That's why I said earlier you could transform it into mole percent or mole fraction. But since I'm using mass fraction, I need to convert it into moles. So that's 100 grams of P1 times 0.65 times the molar weight is 78. And then, that's it. The consumed, well, C6H5Cl uses C6H6, so that's 1. C6H4Cl2 uses C6H5Cl, which in turn uses C6H6. And then last one, C6H3Cl3 uses C6H4Cl2, which uses C6H5Cl, which uses C6H6. So, napakarami ng terms. So, let's start off with C6H5Cl. 100 times 0.32. So this is 112, right? And then 1 mole C6H5Cl. That's done. C6H5Cl. We move on to C6H4Cl2. 100 times 0.25. Yeah. Okay. And then 1 mole of C6H4Cl2. That's worth 46 grams. And then 1 mole of that needs 1 mole of C6H5Cl, but we know that 1 mole of C6H5Cl needs 1 mole of C6H6. Last one. This is for C6H3Cl3. So that's 180 grams. And then we relate it to C6H4Cl2, which in turn re-relate natin to C6H5Cl, which in turn it re-relate natin kay C6H6. So it's very, very long. That's it. And turns out we're going to get 1.14 moles of C6H6. Okay, now we need to do the percentage percentage excess of benzene. Percent excess of benzene is the number of moles fed minus moles out over moles fed. Moles fed, that's 1.14. Moles out is 100 times 0.65 times 1 over 78. Diba? Ito lang din yun. Over moles fed, which is 1.14. Okay, I just realized, ito pala is fractional conversion ng benzene. So that's fractional conversion, that's for letter C. Okay, this is 0.269. Apologies. This is for letter C. For the... Wait, what? Ah, no, this is for letter B. Because the fraction, a percent excess is fed, number of moles fed minus number of moles theoretical over number of moles theoretical. Right? Right. Okay. So we need to find the number of theoretical moles. So with that, I need to get Cl2. Okay. Cl2 balance. In minus out plus gen minus consumed. Stat generated, it did not go out. So in is equals to consumed. What's interesting here is that Cl2 is very close to the C6H6 balance. We just do not include this part. So if we take 1.14 and we subtract it to 100 times 0.65 times 1 over 78, that'll give me the answer. Or you can do this balance as well. So in is 1.14 minus the out term from earlier. This is just a shortcut because the balance is very close to each other. The difference is that the C6H6 has an out term, Cl2 has none, and they're similar to each other here. So this means it's 0.31 mole Cl2. Okay, now we get the theoretical benzene. 0.31 mole Cl2. 1 mole of Cl2 requires 1 mole benzene. So in the end, theoretical benzene is 0.31. So to get the percent excess, the number of moles fed is 1.14. Theoretical is 0.31 over 0.31. Then we multiply it by 100 and we get 267.7. So double the amount. Next, fractional yield of benzene. Again, yield is actual over theoretical. So with that, 0.31 mole C6H6, 1 mole C6H6 chlorobenzene is C6H5 Cl. So that will give me 0.31. C6H5Cl. Okay, so this means that the yield is 0.31 over, well, no, that's the theoretical. Actual is 100 times 0.32 over, wait, na C6H5 cm, 146. And that will give me 100 times 0.32. It's 1 over 146 over, oops, 0.707. That's the yield. Okay, lastly, the mass ratio of the gas feed to the liquid feed. Okay. The gas feed is the Cl2. So we have information on that, 0.31 moles Cl2. Its mass is 70. 1 mole Cl2. But it is said here that the gaseous feed is 98% Cl2. So this is not 100%. This is just 98%. So let's solve for that first. 0.31 over 70. Break that. Okay. 21.7 grams Cl2. But this is just 98%. So to get the 100%, the whole gas feed, we just divide it by 0.98. (22.14). And then the mass of the liquid is just the benzene. We can get that. So 22.14 grams over the mass of the liquid is 1.14 moles. And then 1 mole C6H6, 78 grams. (0.249). That's it. We're done. We're done with the we're done with the molecular balance. Next, we will do extent of reaction and atomic balance.